Hello, chemistry students. Professor Sean McMahon here with our second lecture for Chapter 6, Compounds and the different types of bonds. So last time we covered quite a bit. One of the things we talked about was how to determine from a name, a molecular formula, or from a molecular formula for a name for binary compounds. The two types that we discussed were binary ionic and binary covalent. So again, if you have a periodic table, you should take it out and use it. We'll be using it today. But essentially with your binary ionics, you have a metal and a non-metal. There's a complete electron transfer resulting in charged particles. So we went over binary ionics, metal, non-metal. Binary means two elements. Then we went over binary covalent compounds. That's a non-metal and a non-metal. Because the non-metals share electrons, there's not a complete electron transfer. We can't use charges, so we use the Greek prefixes to determine the correct formulas and names. Then we went to the special types of covalent compounds, which were acids, and we left off with the binary acids. Binary acid is where you have a non-metal essentially with hydrogen, and because the non-metals are so good at taking electrons, even though hydrogen's a non-metal, it can actually take the one valence electron from hydrogen away and produce charged particles. And we went over the binary acids and how to name them. So we actually had the hydro prefix. So here's an example of hydrochloric acid found in stomach acid, gastric juice. And we see that all the binary acids, binary meaning two, hydrogen and non-metal, have the hydro prefix, okay? And then it has the ic acid suffix. So we went over these, and one of the things is for the selenic acid, I want to point out there's something unique about this, that this actually has two hydrogens. So unlike hydrochloric acid and hydrobromic, those are monoprotic acids. So what do I mean by monoprotic? There's only one proton that's released. So when I throw this in water, I produce only one proton and one chloride ion. And why is that? The chloride has a negative charge of 1. Same with the hydrobromic. Oops, I was going to write chlorine. Sorry about that. So how is it different with hydroselenic? Well, why is there two? Well, if there's two H pluses, why is that? That's because selenide is a 2- charge, okay? That's why there's that 2-to-1 ratio. So we talked about how we could use charges. Now, again, I know acids are actually molecular compounds, but again, once we throw them in water, they dissociate and they break apart. That's part of that's what acids do. They give us these hydrogen ions. That's what makes them an acid, even though they're a molecular compound. So here's another example. So first, how would we name this? Well, it'd be hydro. Now this one's special. It actually writes the full name, sulfuric acid. And you might think at the very end, you know, the reason why you have the two H pluses, and that's because the sulfide ion has a -2 charge. What people don't fully understand is there's actually an intermediate step here. And I want to go over that intermediate step because it helps us understand Lewis dot structures, which we'll be doing next lecture, lecture 3. It also helps us understand what we'll be doing in today's lecture, which is we'll be going beyond binary compounds with ternary compounds and talking about polyatomic ions. So I always like to do this where, why is hydrosulfuric acid the way it is? Well, sulfur is group 6A. And again, how do I know that? I got my periodic table. So it has 6 valence electrons. Notice there are 2 unpaired. Each hydrogen has a valence electron, and it has 1 unpaired. So to make everybody happy, the hydrogens want to be like helium, which has the first energy level filled. They want to have a 1s2 electron configuration like helium. So they want to have a duet. But all the other elements want the octets, right? So sulfur wants to be like argon because it has the S and P sublevel filled. So it's willing to share these electrons and form bonds. So that would be the Lewis dot structure for hydrosulfuric acid. Now, when I throw this in water, right, I know eventually what will happen is I'll have an H plus who lost its electron, and we'll say, you know, you lose that electron and you lose that electron. And then I'll have the, you know, the sulfide ion, which gained the 2 electrons from the 2 hydrogens. That's why it has an octet and now a charge of -2. But what we don't see is that doesn't happen right away. In fact, there's an intermediate step. And that intermediate step is one of the hydrogens, right? So sulfur is trying to pull the electrons as a nonmetal away from the hydrogen. And at first, it doesn't pull both of them at the same time. It's easier to do one at a time. So the sulfur actually first only pulls one away. So at first, we would just have one H plus, and what would remain, and I'll draw it, you know, kind of like a Lewis dot structure, is this structure. So again, there's still, you know, this hydrogen's still bound and has 1 electron, and then the sulfur has a 1 odd electron, and it's sharing in this bond. And eventually it'll take this one and form the sulfide ion. But before it does that, it first gets it from just 1. And what ends up happening, because it steals the 1 electron, it ends up getting a charge of -1 rather than -2 right away. And the way you would write this out is HS minus. So, and again, I'm writing the more metallic element, hydrogen's further on the, you know, on the left. I write that first. I end up getting an HS minus. So what is this? So it's not an atom, and it's not an atom because it's not neutral. It's not a compound, right? So it's not ionic or covalent compound because those formulas, those molecular formulas, give me a neutral charge, a net charge of 0. So this has a charge. So this species right here that I'm drawing, this intermediate species, is an ion. Why? Well, it's negatively charged. Okay, so what type of ion? Well, if it's negatively charged, it's an anion. Okay, well, why is there more than one atom carrying this charge? Well, there's only 1 electron that's been taken, and it's still held together covalently. So it's held by this covalent bond, but it's an ion because overall there's a charge that's not 0. Now, is there more than one type of atom? Yes. So this is what's referred to as a polyatomic anion. And that's what this lecture is going to talk about, is when we can have more than one atom covalently bound, held together, but carrying a charge. And because they carry a charge, they're not a compound, they're an ion. So how would I name this ion? Well, if this is the sulfide ion, this would be the hydrogen sulfide ion. It's not complex. It's a hydrogen and a sulfur, but it has an ion. So it's hydrogen sulfide. So hydrogen sulfide is a derivative from hydrosulfuric acid, and it's an intermediate step before both protons are released. So we have to understand that there are these polyatomic anions, and that those can be grouped because they're ions in ionic compounds. But it won't, any It will no longer be binary ionic. It'll be ternary because there's polyatomic ions. So that's what today's lecture. And, you know, just to give you guys kind of an idea, I could literally, you know, I'll have to remove the name here because if you look on the periodic table, sulfur is underneath what element on the periodic table? Oxygen. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. Each hydrogen has 1. They're covalently bound, right? That means they share electrons. But there are some cases where the oxygen may steal an electron from the hydrogen and break this covalent bond and steal that electron and form what is called, and I think a lot of you actually know this, what's referred to as the hydroxide ion. So the hydroxide ion is what? It is a polyatomic anion. What does that mean? It is 2 elements that are bound covalently that carry a charge. So that brings me to now. This lecture, polyatomic ions, 2 or more atoms that are bonded covalently and have either a net positive or negative. The negative is more common, but there are some cases with a positive. So here's a table in your book. It says, okay, these are some, and I know a lot of you are going, whoa, that's a lot. When I was in school, they didn't even lecture. They just gave us 3 pages of tables back and front, and we just had to know it. I'll be a little more gentle. There are some that you just have to know. I don't have any tricks, okay? So I did just show you the hydroxide. That's the OH minus. And that name, you know, it makes sense. It's a hydrogen to an oxide, hydroxide. Another one is the ammonium. Now, some of you may know that NH3 is ammonia. The difference between ammonia and ammonium is there's an extra hydrogen plus. There's an extra proton. So you can see there's an extra hydrogen, but there's a plus charge, right? So there's an extra H plus. So because there's a +1 charge, it has the ion, just like lithium, sodium, potassium. In group 1, they end in the ions. So ammonium has a +1 charge and is derived from ammonia. It just adds another H plus, which happens to also be in group 1A, which has a +1 charge. Cyanide. This one's a little tricky, but I think people always think of movies, you know, bite your tooth, cyanide, I don't know, maybe not. But cyanide is another one you need to know, okay? One that I personally think is the most challenging is the acetate that you're expected to know, okay? Now, the acetate, if you look at C2H3O2 minus, and that could be confusing. A lot of times in organic chemistry, they write it out, the structural formula, based on how it's grouped, and they'll write for acetate CH3COO minus, which is the same thing. There's 2 carbons, 3 hydrogens, and 2 oxygen. What the CH3COO minus tells me is there's a carbon that's covalently bound, wide covalent, non-metals sharing electrons. And then there's another carbon that has a double bond to this oxygen, because oxygen, the bonding pattern, it likes 2 bonds and it has 2 lone pairs like an H2O. And then you have an oxygen with an extra electron right there. So that's acetate. And that's actually derived from acetic acid. What's acetic acid? Well, acetic acid, some books, like our book, writes HC2H3O2, because typically you write the hydrogens in front for acids. But if you take organic chemistry, they'll write CH3COOH, and COOH is indicative of basically a carboxylic acid group. And that extra electron, where they actually got it, was from acetic acid. And what we actually have is this electron actually came from a hydrogen. And we see right here that this oxygen, just like this one, has 2 bonds and 2 lone pairs. And what it does when I throw it in water, it steals that electron from the hydrogen, giving me the acetate ion and a proton. That is the Lewis dot structure, kind of material that will be coming in next lecture. I don't do, typically I only expect students to be comfortable with Lewis dot structures for this course with single central atoms versus multiple. Acetic acid has multiple central atoms. It has 2 carbons, and then it also has an oxygen. So it's a little more difficult, but you do need to know that this is the acetate ion. So I always tell students, look, what you see in red, you have to memorize. Okay, so if that means putting it on a 3x5 card, that's fine. You have to know. But you do have to memorize those particular polyatomic ions from this course. The ones in blue, you have to know. And notice I'm not making you know all of them on this table even. There's more than this, trust me. There's oxalate, there's tons. But like chromate, dichromate, permanganate, those are going to be learned in other courses. But the ones that I have in blue, there's a trick to remember those. And I'm going to show you how to remember the nitrate, the big ones that I emphasize: nitrate, phosphate, chlorate, and sulfate, okay, and carbonate are the 5 big 8s that I want you to know, big time, because there's a trick that I'm going to show you to memorize those 5 big 8s that are going to then allow me to memorize all of these, right? So if I know the 8s, I'm going to be able to figure out the ites, all right? So how? Oh, and the hydrogen 8s. So first, these polyatomic ions that I had in blue, okay, the ones in blue, where I'm going to teach you a little trick, they're called oxyanion ions. And that's because they typically have more than one oxygen, okay? So there are families of these polyatomic ions that are called oxyanion ions, okay? So polyatomic ions, more than one atom, covalently bound, carrying a charge. So in actuality, when you think of hydroxide, if I was to use molecular models, I didn't even think about it. I have my model kit right here. Pays to be kind of, I was kind of showing how here's my water, right? This doesn't show the lone pairs, just the atoms. Here's my oxygen, the 2 hydrogens, but they're covalently bound. If I remove a hydrogen, this is just my hydroxide with the extra electron, okay? But with the oxyanion ions, there's different ways to name them. So you have 2 or 4 member families. So you have the 2-member families where you see oxyanion ions with only 2 different types of ratios with oxygen. So the name for both of these is derived from the nonmetal nitrogen. So I have nitrite and nitrate. Or you have the 4-member families where now there's 4 oxyanion ions with ratios of oxygen to the nonmetal. All of these are derived from the nonmetal chlorine. So I have, and if I just go in order here, hypochlorite from left to right, chlorite, chlorate, and perchlorate. So these are, I'm telling you, these are the ones I want you to know. I want you to know the ones in red, your acetate, your ammonium, your cyanide, your hydroxide. I want you to know the 5 big eights. I'm going to show you the 5 big eights. And then, be comfortable with hydrogen carbonate and things like that. So how are we going to do this? Periodic table. Okay. I want you to get a periodic table out. Now, for non-metal eights. So what do I mean by non-metal eights? This trick only works on the right side of that staircase. So if the central atom or the non-metal is on that right side of the staircase, it's an oxyanion, this trick will work, okay? So typically when I have a non-metal eight or one of the 5 big eights, I have the non-metal and then I have 3 or 4 oxygens, okay? So don't worry about the number of oxygens just yet. I just want you to look at the name, tell me the non-metal. So if I see phosphate, it's not phosphide, so don't get confused. This is, whoops. This is phosphide. That is a monoatomic. That's what we learned when we were doing the binary last lecture. That's a monoatomic anion. We're doing polyatomic, and they have 8 endings, not I, okay? So phosphate, it has phosphorus and oxygen. 3 or 4, because it ends in 8. I'm going to get there. Just give me a chance. Sulfate, sulfur and oxygen. Chlorate, chlorine and oxygen. Carbonate, carbon and oxygen. Nitrate, nitrogen and oxygen. So now, if I go to my periodic table, I see this little staircase, right? And what I want you to do on the staircase is find where your phosphorus is and your arsenic and draw a line. Find sulfur, selenium, and tellurium, draw a line, and then put a line right there. And what I draw on the periodic table is a 4. So basically, if the non-metal is on that 4 that I draw on my periodic table, it means that that polyatomic 8 ion, right, has 4 oxygen. So phosphate is on the 4, there's 4 oxygen. Sulfate, it's on the 4. Chlorate, it's not on the 4. Nitrate, not on the 4. Carbonate, not on the 4. Okay, so the 4 is very useful, okay? Next, phosphorus. Well, it has a 3- charge, just like phosphide. Sulfate has a 2-, just like sulfide. Chlorate has a 1- like chloride. Where is it tricky? We actually see that there's some inconsistencies, like with borate. How do I know this is borate? I have boron. I'm not on the 4, so I have 3 oxygen, but the charge is a 3-. Carbonate is a 2- charge. So it's not a 4-, okay? I know that's easy to think, but it is not a 4-. So just know that. Nitrate is a -1. So it's easy to be kind of skewed away and think it's nitride, which has a 3-, but it is not. So those you kind of just have to know. You could also fill it on the periodic table, because you could do, here's -1, -2, -3, right? And then you kind of have a -2 here, -3, and your 1 exception. So 1, 2, 3. All right. So how does this help? Well, if I look at this, that takes care of a lot on this table that I expected you to know. So you could either use the 4, or you can memorize by using a 3x5 card. But really, using the 4, you just need to draw it on the periodic table. And it could help you for stuff that's not even on the table that I don't even expect you to know, like bromate, right? So if I tell you, hey, write out bromate, you would say, okay, well, bromine must be the non-metal. It's got oxygen because it ends in 8, but it's not on this 4. There's got to be a 3, and it's a -1 charge. I don't expect you to know bromate, but what I'm showing you is the power of the 4 can help you derive it. Okay. So those are the ones I want you to know in blue. Okay. So we'll see. Chlorate. It's chlorine. It's got 3, not 4. Why? It's not on the 4. It's got a -1 charge. Carbonate. It has 3 oxygen. Its charge is a little goofy. It's that 2-, but we'll be okay. Phosphate. Phosphorus, it's on the 4. It's got 4. It's got the same charge as phosphide. Sulfate, right? If I look at sulfate, it's got 4. Why? It's on the 4. It's got a 2- charge. Nitrate, it's got 3 because it's not on the 4, but it does have that -1 charge. So I personally would say use the 4. I learned this when I was teaching. I wish someone would have showed me. It would have saved me a lot of headache. Okay. Now, why is the 4 helpful? It helps you know the 5 big 8s that I absolutely want you to know. But now, if I see something that says hydrogen sulfate, it's basically an SO4 2- plus an H+, which gives me an HSO4-. That's hydrogen sulfate or bisulfate. Also, if you look, hydrogen carbonate, bicarbonate. How is that different? Here's carbonate, CO3 2-. If I add an H+, what do I get? Hydrogen carbonate or bicarbonate. That's the power of the 4. It gives me the 5 big 8s so I can derive these hydrogens that I attach to these 8s. Let's do a greater review because you need to know, when is it the 2-member family? When is it the 4? How do I know? The big thing is if you know the 5 big 8s. So here you have to know, like when we did the transition metals, I said, I don't make you memorize the charges for the transition metals because we can use the Roman numerals. Here, you don't have that luxury. You have to know if the 8 has 3 or 4. The reason why you need to know if the 8 has 3 or 4 oxygen is because the ite ion has 1 less than the 8. And it's going to be different if it's sulfite, right? The number of oxygens versus a nitrite, because sulfate has a different number of oxygens than nitrate. So nitrate is NO3-. Why? It's not on the 4, so it has 3 oxygen. So nitrite, the ite means 1 less. It's got to have 1 less oxygen. It's NO2. But why do you need to be careful? Sulfate is SO4 2-. Okay, how do I know that? I drew a 4 on my periodic table and sulfur is on the 4. So sulfite, it's 1 less than 4 is SO3 2-. That's the power of the 4, right? It tells me, because now the sulfite only has 3 oxygen, but the nitrate has 2. Why? Because nitrate has 3, it's not on the 4, and sulfate has 4, it is on the 4. What about 4-member families? This typically only happens with chlorine, bromine, and iodine. I only really want you to know for chlorine because it's derived from chlorate, one of the 5 big 8s that I want you to know. So you need to know this is chlorate. Why? Well, it's an 8 ion, which means it's a polyatomic oxyanion, and it's a non-metal of chlorine as the central atom, and there's 3 oxygen because it's not on that 4 that Professor McMahon told me to know. Okay, so how is that helpful? Well, there's chlorate. There's chlorite. We already learned this. Chlorite, ite is 1 less than 8. If I know chlorate is 3, then chlorite has to be 2. But there's 2 more. If there's one with 2 less oxygen, again, this is only going to happen for chlorine in this class, right? So I went from 3 to only 1. It's hypo. So now you have not just the ite suffix, but the hypo prefix. So if you've ever heard the hyper person has a lot of energy, where hypo means you're less energy, or hypoosmotic, or, you know, so just think hypo means not 1 less, but 2 less. Okay. So that's 3 of the 4 members of this family. The 4th is, now I don't have 3, I have 1 more. So I still keep the 8 suffix. It's not ite because I'm not less, I'm more. So I keep the 8, but now I add the per prefix. I know you would think hyperchlorate, but no, it's perchlorate. Why per? The very first lecture of this chapter, does anyone remember what I said the name of this was? The H2O2? Because remember, this is the molecular formula, and I said the simple formula is HO, empirical formula, but it's actually H2O2 because when we do the Lewis dot structure, right, we have hydrogen. Here's my oxygen. Here's another oxygen. And here's another hydrogen. And then there's a bond there, a bond there, and a bond there. It's a molecular compound, all nonmetals. What is that called? Hydrogen per oxide. Why? Because it has 1 more oxygen than H2O. So that's hydrogen peroxide. The per means 1 more. That per prefix. So when does it get tricky? Okay, I already dealt with the binary ionic. I realized that I always have to have a periodic table to identify if it's ionic. And the best way to do that is if there's a metal in there or some charged particle. But there's also binary ionic with transition metals. So if it's in the valley, it could have more than 1 charge. So I'll have to denote that with Roman numerals. Or if I see a Roman numeral, I have to be aware that that's telling me the charge of that metal. But now, on top of those rules, I have to layer this, you know, polyatomic ion. But we can do this, right? So when I look at this, like if I first look at a formula, I first need to figure out, is this ionic or is this covalent? Because if it's ionic, I have to think of charges for ratios. If it's covalent, I have to think of prefixes, right? The mono, dot, all that. So if I look, because there's a metal, I know it's ionic, right? Because covalent would just be non-metal, non-metal. So I know this is ionic, and I look and I say, hey, this is sodium +1, and that will help me derive that this is CO3 2-. Now, how do I know it's 2-? I need 2 +1s to make it neutral, so that has to be a 2-. So I know that's carbon. Is it carbonite, carbonate? What is it? It's carbonate. Why? It's not on the 4 that I told you. Or you could just memorize it, but that is sodium carbonate. What about the next one? Magnesium hydroxide. Now I have the name and I have to figure out the correct formula. This is hard because remember, students go boom and they think they're done. Don't do that. When you see that it's magnesium and hydroxide, you're like, oh, there's a metal. Ding, 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 ding. I need to think of charges. So I would say to myself, magnesium's in group 2A. It's a 2+. And then I go hydroxide. Oh, that's the one of the 4 that Professor McMahon said I should know. Here's my hydroxide. So I'm going to do a crisscross, but Because I need two hydroxide groups, I cannot forget to put parentheses because I need two groups of OHs, not one, to cancel out that 2+ charge. Potassium nitrate, potassium, K, group 1, it's a metal. So now I'm like charges. Potassium's a +1. Okay, it ends in 8, so it's not a monoatomic ion. It is not this. That is nitride. Okay, the ides are your monoatomics. Monoatomic ions. Remember, your 8s are the polyatomics. So nitrate means, okay, polyatomic, there's nitrogen and there's oxygen. Ooh, is there 3 or 4? Because it's an 8. Oh, it's not on that 4. So there's 3. And this is one of the goofy ones. It's a -1, not a -3. So it's going to be a 1-to-1 ratio. Now this next one, I need to name it. So CO. It's not carbon and oxygen because it's a lowercase o. So this is one element. That's the elemental symbol of one element. And that element, when you look, is in the valley. Okay? It's atomic number 27 in your valley. So because it's in the valley, you're like, oh, okay, it's a metal, so it's ionic, but it's a type 2, right? And what do I mean by type 2? It's a transition metal, so it has more than one charge. Because it has more than one charge, I have to incorporate a Roman numeral. So how do I figure out the Roman numeral? This is probably the hardest one of all. These two are the hardest. No, this one's the hardest. Okay. The reason why this one's the hardest is I have to know the charge of phosphate to figure out the charge of cobalt. Okay. Because I didn't memorize all the charges for cobalt, or maybe you do, but I would tell you to know the charge of phosphate. So you're like, all right, phosphate. How do I know it's phosphate? It's on the 4, it had a 3-. So if it's a 1-to-1 ratio, this cobalt has to be a 3+, because to cancel out the 3- from the phosphate, which is on that 4, I need a 3+. So it's got to be cobalt 3-phosphate. Yep. Now with nickel 2 sulfate, I know it's nickel. And that Roman numeral, I mean, I don't even have to look at the periodic table, but you should. You see that the nickel is in the valley as a transition metal, and there's more than one charge. And that's why they gave me that Roman numeral 2. So I know it's nickel 2. Then sulfate. Okay, it's an 8 ion, which means it's polyatomic. So where am I looking? The freaking 4. So I go and I go sulfur. It's either 3 or 4 because it ends in 8. It's 4 because it's on the 4. It's a 2- charge. It's a 1-to-1 ratio. Yep. So then you go to the next one and you think, all right, what do I do now? Well, this is sodium. I know that. It's a +1, but this is not chlorate. The reason why it's not chlorate is because chlorate is ClO3-, right? Because chlorine's not on that 4. So it doesn't have 4 oxygen. The chlorate has 3. So this is chlorate. Well, what's this? It's 1 less. So that means it's chlorite. So hopefully that helps. And again, it's tricky, but that's why you do homework problems. I mean, there are a lot of these for your homework problems, and hopefully that helps out. Now, with the polyatomic oxyanions, it's a lot easier to derive the second type of acid. So remember, I said covalent compounds, there's special ones. They're the acids where you throw them in water and they dissociate and they give you hydrogen ions. The easier one we did last lecture with the binary acids, easier because it's binary, meaning there's only 2, hydrogen and a non-metal. We did that in the very beginning where with the binary acids, we have the hydro prefix and the root of the nonmetal. Okay, with oxyacids, now there's the hydrogen that's going to dissociate to give me the proton. There's the nonmetal, and then there's the oxygens because it's an oxyanion. But we can use the 8 to derive the ic acid. So I can use the ite to derive what is called the us acid. So the 8 ion derives the ic acid. The ite ion, remember, ite is 1 less than 8, derives the us acid. So here are some examples where I use the 8 oxyanion to derive the ic acid. So here's nitric acid. How did I derive that? Well, there's nitrate. How do I know that's nitrate? I drew the 4. Nitrogen's not on the 4. It has 3 oxygen. Nitrate has a -1 charge. So I need to add 1 proton or H+ ion to make it neutral. So the nitrate derives the ic acid. Sulfuric acid. Now, don't say hydrosulfuric. Remember, whoops. This is hydrosulfuric. It has the prefix hydro because it's binary. This is not binary. There's an oxygen. It's an oxyacid. So there is no hydro prefix. It's sulfuric acid. So why? The 8 ion derives the ic acid. What do I mean? Sulfate. Why is there 4 oxygens in sulfate? It's on the 4. So sulfate gives me, if I add, so because this is a 2-, I need 2 H+ to make it neutral. So there's my sulfuric acid. By the way, this was the 3D model that I first showed when I was introducing chemical formulas, the sulfuric acid. You can look back on the prior lecture. Chloric acid, that's derived from chlorate. Perchloric, that's derived from perchlorate. Carbonic, derived from carbonate. Phosphoric, derived from phosphate. Notice, right? What is really, so we see that sulfuric acid and carbonic acid are diprotic. What do I mean by diprotic? They have 2 hydrogens that can be released as an acid, right? The nitric acid, the chloric and perchloric, because the oxyanions are negatively, they're monoprotic. But what do we notice about phosphate? Phosphate has a 3- charge, which results in phosphoric acid being triprotic, meaning I can give up to 3 hydrogen ions because it's triprotic. Can we do this where the ite derives the us acid? Yes. Nitrous acid is derived from what? Nitrate. How do I know that this is nitrate? Well, this is nitrate. How do I know that? The 4. The 5 big 8s. So this is 1 less oxygen. So nitrous acid is derived from nitrite, and it's HNO2. This is chlorous acid. Why? This is chlorite. This is hypochlorous. Why? This is hypochlorite, right? So the ite suffix is replaced with the us acid when I add the protons, but I keep that hypo prefix because this is 2 less rather than just the 1 less from the ic acid. And then sulfurous is from sulfite. So types of bonding, okay? We talked about, again, the ionic bond, they're really formula units. They're like the empirical formulas, the simplest formulas, right? There is no molecule of sodium chloride. There's not a one sodium and one chloride that are just by themselves. They're in these complex lattice structures, these crystalline structures. But the ratio, the formula unit, is a 1-to-1 because sodium's +1 and chloride's -1. So that's why we just write NaCl. With molecular compounds or covalent compounds, we actually have individual molecules. So they have covalent bonds. There's no charges. There's not a complete electron transfer. There's sharing, right? So like in the case here. And it's non-metal with non-metal. Okay, so you actually do form individual molecules. So for covalent compound, that's the plural of the singular of molecule. That's not really the case with ionic compounds. Ionic compounds, the singular of that would just be the formula unit, but there's actually no molecule for ionic compounds. We did talk about the electron transfer. Remember that metals form cations by losing and non-metals gain. And the metal transfer, right, to the non-metal helps them both achieve that noble gas configuration. So here I go back to the Lewis dot symbol, and I actually use the element sodium, which has 1 valence electron, because why? Group 1. Chloride, group 7A, so it has 7 valence electrons, right? And they both want octets. Well, if sodium loses its 1 valence electron, it becomes like neon, right? Because sodium actually is a 1s2, 2s2, 2p6, 3s1. We learned that in chapter 4. Why is it 3s1? Third period, S block, first position. So if I lose this 1, then I have my second energy, the S and P sublevel filled exactly like neon. I'm happy. So that's exactly what it does. But when it loses a negative, it becomes positive, right? Chloride is 1s2, 2s2, 2p6, 3s2, 3p5. If it gains 1, it becomes, oh, actually, my bad. It's, yeah, no, that's right. It becomes like argon. So when it gains this 1 negative charge, it becomes negatively charged. It's a 1-to-1 ratio. What if I wanted to figure out this electron transfer for sodium oxide? Now, sodium oxide, how do I know this is ionic? Sodium is a metal. This is a non-metal. Oxygen. Oxygen has what? 6 valence electrons because it's in group 6. So it has 2 unpaired. 2 sodiums are going to get rid of their 1 electron and actually pair up. So let me actually do something here. This electron and this electron are going to pair up with these unpaired ones and give it a octet. And that's why, because it gains 2 electrons, it gets a 2 negative charge. So the reason why ionic bonds are not sharing, there's a complete loss and gain, a complete electron transfer. That's why you have charges. But the charges cancel each other out to produce a neutral compound. And that's how we got those ratios for the formula units, or, you know, the formulas, chemical formulas. Molecular compounds, again, the electrons are shared, so we're kind of reviewing it. They share to receive the noble gas configuration. So here's an example of molecular compounds. We have hydrogen, which has 1 valence electron. Oxygen, it has 6, 2 are unpaired. So I need 2 hydrogens willing to share their electrons. But we don't just draw dots for molecules. We'll actually say, well, if this is, you know, if these 2 are the shared, we just draw a line. And if these 2 are shared, we draw a line. The line shows a bond, which is the direct overlap of half-filled orbitals, but basically it's a way to share those electrons. That's what the bond is, and we draw a line. If it's not shared, because we don't need to, we draw two dots, and those are referred to as lone pairs. Okay. Hydrogen's happy because it wants to be like helium, and that is the one noble gas that doesn't need the octet. It simply needs a duet. But the oxygen's happy because it has an octet, right? It has its second energy level filled, which can have 8 valence electrons, 2s2, 2p6, so the s sublevel and the p sublevel are filled. And again, the bonding pair and the lone pair, the bonds are going to show as lines. So that's kind of the sharing of electrons. So we have, the sharing of electrons. Don't just do, I tell students for shared pairs, you want to show lines. Okay. Lone pairs that are unshared, you will do the dots. And they don't need to share this because they already have their octet, and the hydrogen doesn't want more than one bond. Hydrogen never wants more than one bond. You will never have more than one bond for a hydrogen, ever, because it can never go beyond a duet. So here I have an example of nitrogen. This goes back to the bonding patterns that I talked about. Nitrogen is group 5A, so it has 5 valence electrons. So if we were to start with nitrogen, 1, 2, 3, 4, 5, we see that one pair is already paired, and that will be my lone pair because I don't need to share it. It's already happy. The 3 unpaired ones will bond with unpaired electrons from 3 separate hydrogens, and they would overlap their orbitals, and then they would be shared pairs right here. And those shared pairs we draw as bonds. It's the same with carbon. And this is why carbon is such a great little central atom, because it can have 4 bonds. So it can bond more things around it, right? So carbon, group 4A, it has 1, 2, 3, 4 unpaired electrons. It needs 4 more electrons. So if 4 hydrogens are willing to share theirs, it'll be happy. And then I draw 4 lines. So this discussion on reviewing ionic compounds, molecular compounds, and the exchanging of electrons, and finishing up our discussion on nomenclature of the polyatomic ions that are actually held together by covalent bonds, but have a charge, right? Because there's an extra electron, or ions. This ties into the next lecture, which is where we will continue doing what we are doing right here and drawing structural formula and what is referred to as Lewis dot structure. You will see in the next lecture, we'll start making it a little more complicated, and I'll give a set of rules for you to follow while you make these Lewis dot structures. And then over time, the rules will become second nature and you won't need them anymore. But in the beginning, when you work on the problems, have the rules out, follow them, and do step by step. So I want to thank you for tuning in and being patient as always. And I look forward to seeing you in the next lecture where we'll continue our discussion on covalent compounds and drawing molecules using Lewis dot symbols. Okay, thank you so much.